We have an example here where we have one mass m that moves along in horizontal motion, but it's attached to two springs, spring number 1 and spring number 2, that have different resting lengths, x1 and x2, but also different spring constants. And so our job is to find the equation of motion for the two spring system shown. And we're going to apply that three-step process for each of the springs to determine the proper way to represent these springs within our models. And so we start out, as always, by defining our reference frame and coordinate. And here we have our reference frame I in the direction of travel, and then we've defined our coordinate x so that it's positive as the mass moves to the right, negative as it moves to the left. To find the equation of motion, we need to have some elements we can insert into Newton's second law, which is F equals ma. And to take care of the left-hand side, we have to draw a free body diagram. And so our free body diagram of our mass, or of our block rather, is really simple. It's a block, but we've got two spring forces that are applied here. The spring force on the left, remember we're going to draw our spring force from the point of attachment to the mass. And so our first spring force is F sub S1. And then for our second spring force, we're going to do the same thing. We draw the arrow from the point of attachment to the mass itself. And so this will be pointed in the opposite direction. So it's F sub S2 for each of our spring forces. And then remember, the second step is simply to say that our force is equal to negative spring constant multiplied times the displacement. And so for our first spring, F sub S1 is equal to negative K sub 1, and it's x minus x1 represents the displacement from the resting length. And for our second spring, F S sub 2, we're going to write this in a similar manner. So negative K sub 2, and then the difference between our distance here and the resting length x2 is this distance is represented by the expression d minus x sub 1, and then we're going to subtract our resting length x sub 2. So now we insert these into Newton's second law, which says F equals ma, and so for our first spring, it's F S sub 1, and this is going to be a positive because on our free body diagram it's pointed in the positive direction with our coordinate. But for our second spring, F S sub 2, this arrow is pointed in the opposite direction as our positive coordinate, and so this has a negative sign, and it's equal to our mass, x double dot. And now we insert the scalar equations for each of our spring models, and we get negative k1 x minus x1, and then we get a negative negative. So when we insert this model, it becomes positive k sub 2 d minus x minus x2, and this is all equal to m x double dot, and then we get our final equation of motion. And so what we have here is an equation of motion that looks similar to the single spring that we did in the last example, in which we have a scaled spring constant multiplied times the displacement from the resting length. But now, because we've got two springs, this is a more complex system, and we can be confident now that these signs are correctly applied given the coordinate that we've chosen and given all the dimensions of the system. And so I encourage you to go back and do the exercise of where you say, you know, if this block moves to the right, what should happen to these forces? Should my force be positive? Should it be negative? Which direction should it be in? And move it to the right, move it to the left, and then convince yourself that you've got the right answer. And using this process, you'll be able to get the right signs every single time.